Hello, my name is Anna Boscarino. I am a doctoral candidate in Educational Technology Leadership at NJCU. Today we will learn about z-scores. According to statistics, for those who think they hate statistics, z-scores are a type of standard score you will see most often in your studies of statistics. You will also learn how to calculate it and how it is used in education. We will also discuss how it is used in studies and the steps researchers take when using z-scores. Lastly, I will demonstrate how to calculate z-scores using SPSS statistical software. What is a z-score? A z-score represents a measurement of variance between the population mean and an observed data point. In other words, how far is the observed data point from the average? This could be a single data score or the mean of a sample population, usually after some type of treatment and research. It is a type of standard score, meaning scores are calculated in standard deviation. Most people have a good understanding of what one or two standard deviations from the mean represents and how to calculate them if they are provided with the mean and standard deviation. For example, the Stanford-Binet IQ test has a mean of 100 and a standard deviation of 15. Most people with a basic understanding of statistics can calculate the score at one standard deviation before and after the mean to represent 68.3% of the population, with a range of 85 to 115. Most people will also know that a score of 115 is exactly one standard deviation above the mean, which means that they score better than 85% of the population. But where exactly would a score of 122 fall, and how did that person do in comparison to others? To understand this, we calculate the z-score. The formula for z-score is x minus mu divided by sigma. You first subtract the mu, which represents the mean of the population, from the observed score. Next, you divide by the sigma, or the standard deviation, to obtain the z-score. In this case, a score of 123 minus 100 is equal to 23 divided by 15, which is equal to 1.533, which means the score of 123 is 1.533 standard deviations away from the mean. We know the person scored better than 84% of the population, but less than 95%. To find out the exact percentile, you can either do some complicated calculus or just refer to a z-table. These are easily accessible on the internet, or you'll find them in any statistics textbook. I found this table on a site created by a professor of statistics for others to use for teaching or research purposes. The reason why I like it is because it gives you the z-scores for the cumulative area side by side with the p-scores for a one-tail test. The cumulative scores represents the area left of the observed point. You would use this column when you want to find percentile. It also gives you the score for a one-tail test in the second column. If you need a two-tail test, you would just double the number. So here, you go to 1.53 and you will see a cumulative p-value of 0.9370, or a one-tailed test p-value of 0.0630. Let's take a closer look at what that means. Here we see the bell curve with a mu of 100 and a standard deviation of 15. Notice that we denoted the data points up to 2 standard deviations below and above. Our observed score of 123 on the IQ test lands at 1.533 standard deviations away, with a cumulative p-value of 0.937 or 93.7%, meaning they scored the same or better than 93.7% of the population. The one-tail p-value was 0.063, which means that 6.3% of the population had a better score than 123. If you double the value, you get a two-tailed p-value of 12.6, which means that 12.6% of the population had a score as extreme on either side of the mean. To summarize, a person with an IQ of 123 did better than 93.7% of the population, with only 6.3 doing better than them and only 12.6% having a score that deviated from the mean as much or more. Now let's turn to an example of z-scores in research. A researcher begins by selecting a phenomenon they want to study. Once you are set, you establish the null hypothesis, stating there is no difference between the control and treatment groups. Hypotheses are always stated in mathematical terms. The null hypothesis, which is referred to as the HO, is mu of population 1 is equal to mu of population 2. Next, you establish the alternative hypothesis, or the HA. If you were doing a one-tailed test, you would say that the HA is mu 1 is greater or less than mu 2. If you want to find a difference on either side, you conduct a two-tailed test and state that the HA is that mu 1 is not equal to mu 2. Next, you want to establish the alpha level. This is the probability of having a type 1 error where you incorrectly reject the HO when you shouldn't have. In other words, if you set your alpha level at 0.05, you would only get that observed score due to random variance only 5% of the time. In all other cases, it suggests that the variance was due to another factor, hopefully the treatment. Now, while 0.05 and 0.01 are the most frequently used alpha levels, it doesn't mean you can't use a different critical value. The situation should dictate which level you use or how much risk you are willing to take. Next, you calculate the z-score. The formula here is slightly different when you are looking at two populations. The mean of your treatment group, or X bar, is subtracted by the general population or control group mu, divided by the standard deviation, or sigma, which was divided by the square root of the sample size. Next, you evaluate your p-value to determine if you will reject the null hypothesis based on your findings. Let's look at an example. Here we have the IQ of students enrolled in an honors ELA class. We suspect that their IQ is higher than those of the general population. We created the HO that the population is equal and the HA that the mean average is higher than the general population. We set an alpha level of 0.01, which means that any z-score greater than 2.58 will result in us rejecting the HO. Next, we calculate the mean of the scores for the students in the class and get a mean of 115. Now we just plug in the numbers, 115 minus 100 divided by 15 divided by the square root of 30. When you calculate it, you get a z-score of 5.47, which is much greater than 2.58. Now let's take a look at how to calculate z-scores for a given data set using SPSS statistical software. To compute the z-scores of a given data set, you want to begin by opening your data set in the SPSS software. Next, you want to go to the Analyze tab and select Descriptive Statistics. From there, you want to hit Descriptives and a text box will pop up. You should see your variable name for your data set on the left side. Click on the arrow to move it to the right side for analysis. You also want to select the Save Standard Values as variables at the bottom. Select OK and the program will compute the mean and standard deviation for the data. When you go back to the data set, you will now see the z-scores, which are also known as standard scores, next to the original score. If we look at number 26, which has a score of 100, you can see this individual actually scored approximately 1.8 standard deviations below the mean. If you recall, 100 is the mean of the general population. Now, just because you get standardized scores doesn't mean that the data is normally distributed. To see if it is, you can go to the Graph tab. Select Graphboard Template Chooser. Next, select your variable and histogram with normal distribution. Click OK. Now we can look at our histogram and see it's not quite normally distributed. As you can see, using SPSS software to compute z-scores is easy. Thank you for joining me, and I hope you have a better understanding of z-scores and how they are used in the educational field.